Good afternoon and welcome everyone. Thank you for joining us for today's webinar. My name is Raghavendra Krishnamurthy, working at the Motion Analysis and Vehicle Engineering Division of TESCON as Technical Sales Manager. To tell you in brief about our company, TESCON been a supplier of research equipment for passive safety to the Indian automotive industry for over 25 years. TESCON is a distributor of Seattle Safety USA for destructive and non-destructive vehicle crash testing systems. Today we have with us Mr. Philip Tolke, Managing Director from Seattle Safety Europe, who will be the presenter for this webinar. Let's welcome him. Welcome, Philip.
Thank you very much for joining us today for the webinar. It was organized by our Indian representative, TESCON, and I really appreciate you taking the time to be with me today and to listen to my presentation and afterwards to have some questions. My name is Philip Tilke. I'm responsible at Seattle Safety. I'm located for the Indian market and the European market. I'm located in Germany, and so from the time zone that fits pretty well. I wish you good afternoon. And what I'm going to explain to you today is, wait a second, there's someone calling. Rubbish. Hi. Yeah, that's fine. But I hear that the rest of the people can connect. I started. I started. Okay, I already started. Okay, I go over it now. Okay. So Seattle Safety, I'm responsible for the European market and for the Indian market. And what I'm going to show you today is an overview about one very specific product we are selling, which is barrier labs. I'm going to show you a little bit about Seattle Safety too, but that's just the first few slides. And then afterwards, I'm going to deeply go into the technology we use to do crash labs. And I'm going to show examples from existing customers, from future customers. So I guess you're going to get a pretty good overview of what we are capable to do. Some words about Seattle Safety. We are a privately owned company. The owner of our company is an engineer called called Tom Whitman from Seattle. His background is the aerospace engineering industry. In Seattle is Boeing. So the first sleds we produced were produced for seat testing at Boeing. And then afterwards, we started building acceleration sleds for the automotive industry and for other applications. In 2010, we started doing crash barrier labs. There was one very important project for us. That is a Porsche project in Germany, where Porsche asked us to equip their very short lab with a new technology that they could be able to run very high-speed tests in a very short lab, and that was very successful. And based on this development, we built crash barriers from the servo sled product, which I'm going to show you afterwards. We have already 110 systems on the market. From the barrier labs, I would think the number is about 7 or 8 on the market. We have 50 people working for us in the US, certainly main quarter, then in Germany and in China. As I said, our owner and lead engineer is a very person who is very much into development. So his vision is really providing innovative solutions of unparalleled value to our customers. So that's something like Porsche did. They come to us, say we have a specific question, we have a specific an issue which we need to deal with, and then we are coming into the game and developing something specifically for them. And afterwards, we use this technology to go to a wider market, like we do with our barrier products. So, short overview of our products. Crash barriers, I already mentioned. Decelerator sleds, typically used for aeronautic seats anymore. Servo hydraulic sleds very important product for us, our bread and butter product. 110 systems worldwide. I think in India we have 4 systems sold at the moment. Lighting systems, LED lights is what everyone wants to have at the moment. We offer a very good and affordable LED light system with our barriers and with our sleds. And certainly we have some auxiliary crash related equipment. And most important, and that's why I really emphasize on this, is service and support. So we're having service and support from Europe and from the US. So all our customers are getting in-time service and very proactively. Service LED, I'm just going to show a few pictures. Here you see a service LED with an LED light, which we manufactured. And certainly the full crash vehicle barriers, which is the topic for today. Customer list, I'm going to share this presentation afterwards. If you're more interested, go through our customer list. You see here 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 systems already on the market for our barrier systems, and certainly we have a global footprint. That's so important at the moment, especially since many of our customers having a sled in the US, having a sled in India, in China, we want to have the same results, and that's why they all go for our sleds and for our barrier systems. But now let's start to look into the full vehicle crash barriers, which is the topic for this meeting today. There was a reason why we went into this business. There were 1 or 2 players in the market before. As I mentioned before, Porsche approached us, said, we need a better system, we need something which fits into our facility, which is tuned for us. And so, but why do we need better systems at the moment? I think the most important topic to understand is that the accuracy is what's driving crash barrier systems to get refurbished or new ones at the moment. So the technology that is used in older crash labs comes from the 70s, I would guess, 70s, 80s perhaps, and so some things changed since this time. And for example, it is the very high accuracy of the impact position. You want to be able to hit a target, a crash barrier, or a vehicle which you are hitting with a trolley within a few millimeters range. And that means that you can't allow for a free run of the car between decoupling from the rope to hitting the barrier of more than perhaps 1 meter. Because 1 meter is the free running of 1 meter means that if the car is pretty good aligned, you're going to hit the position where you want to hit it, plus minus 10 millimeters, I would guess. Then very important too is with the new requirements for car-to-car crash, it's very important, and especially when you use 2 motors for car-to-car crash, it's very important to synchronize the 2 motors. Because if you look at a very high speed hitting a very low speed car, perhaps even frontal to side impact, then you need to synchronize the cars up to 2 milliseconds in order to be able to hit again this plus minus 20 millimeters impact point. And 2 milliseconds means it needs to be very accurate at the right position with the right speed at the right time. And that's what the barrier system needs to do. It needs to have a very good control which positions the car at the right position, hit the impact point at the right time, because both cars need to be at the same time, at the same moment, and certainly both cars should have the speed they're supposed to have. The other topic why a new barrier system technology is needed is new load cases. We recognize that the vehicles are getting bigger and more heavy, and that the test speed is getting higher. So we are doing, and I'm going to show you data afterwards in the presentation. We are doing tests with 3.5 ton vehicles, and we do tests with 25-ton vehicles, but that's different test kind. So we're doing 3.5 tons, for example, impacts a wall with 100 kph, and depending on the distance you have for acceleration, this is a pretty challenging task. For this, you need more powerful electric AC-driven motors. Why AC-driven? Because the controllability again. We need to be able to control it very, very good and very, very much in order to hit the right position at the right time. The higher accuracy of impact speed. In earlier times, customers were happy if they could do 0.5 kph as impact speed. At the moment, you wouldn't be able to sell 0.5 kph anymore. At the moment, customers are asking for 0.2 or even 0.1 kph impact speed deviation, maximum deviation. That comes from very good simulation departments. The simulation departments very often drive the crash test departments now because they want to really compare the simulation they do in CIE to the crash barrier testing. And so they want to have a crash test within a very, very high accuracy of 0.2 kph, for example. High speed feedback loop. In order to be able to control your accelerating car to hit at the right time at the right place with the right speed, you need to control this car during the acceleration. It's not just accelerate until you hit the wall. No, because we need to do closed loop. So we need to measure what is the speed after 10 meters of acceleration and 50 meters of acceleration. And then we can predict what's the impact speed going to be. Then we can drive backwards a little bit the power so we have the right position at the right time. And certainly very important too, again, because the simulation departments have such a fantastic way to look at vehicles during the crash. They want to have a better view from the pits, from the window, from the film pits below the car. And so we developed a film pit with no cross member, so it's a very, very good view from below without lots of cross members or structure hindering the view to the bottom of the car. So the basic principle of a crash lab, I'm sure you all know this, but I want to shortly explain because later I'm going to use terminology which comes from here, is a loop of rope. On the loop of rope, we have something we call a skate. The skate is fixed to the rope, and the skate is pulling the vehicle towards the block. Then you have a film pit in front of a block, and you have the crash block. That's where you hit against. Or you have a film pit here, and you have a side crash, for example, on a standing car. Behind the block or on any position, we have a motor which is accelerating the car and which is controlled by a control system. Short video. That's exactly one of these crash labs I'm talking about at the moment. It's just a single track crash lab. You go to one direction and you hit a block or another objective you want to hit with the barrier. So there are different layouts for a barrier, possible layouts for a barrier. The one we've seen before is exactly this. This is from a company I used to work for, Concept in Austria, and this was our crash lab in Austria. You see on the back there's a block here. Behind the block there's a motor and the drive system. You see some film pits here, and the car's accelerated against the block. Then the more new design is looking like this, I guess. So that's we're talking of a crash arena. That's driven by the fact that you want to be able to do car-to-car crash. So you want to have two cars, one's coming from the right, one is coming from the left, and you want to have these cars crashing against each other or against an object which is standing on this big film pit here in the middle. The big advantage is you just need crash light once. Crash light is LED light is expensive, so if you can work with one crash light, that's better for you. And then you have this movable crash block. So in case you don't want to do a car-to-car crash, this block can ride into the crash arena, is going to be positioned behind the pit, and you're going to have an impact point. Here we say crash arena is 30 by 30 meters. Then another layout for a typical crash arena is here. Here, this is a customer, and that's Ford in Germany, who's just getting a barrier from us. They have an old building, which is the the rosé part here. That's the old building with a crash block and a drive system and a pit. And they wanted to be able to do car to car. So what we are doing at the moment is we are building the whole system new, and they get this crash arena here, and they get another track. 120 meters is pretty much what you want to have to be able to accelerate with a maximum acceleration of 0.2 to 0.3 G until you hit, because you don't want your dummies to jump to jump around in the car by very high acceleration. So again, here it's the same constellation, but in this case we have a second motor, and the second motor is also driving an angular track, which is able to hit cars coming from here or from here, depending on what kind of load case you want to run. Why are we using this kind of crash arena style? Is shown on this picture. On the top picture here, you see the zones which are here, which have different colors. These zones we call crash influence zones. These are areas, we looked at all the load cases going to be happen on this crash barrier lab, and looked at the position before and after the impact. And this is a position where a car or a trolley could be after the impact, because it's sliding away, because it's rotating away. So here you see that doesn't fit into a small room. So we decided to go for, that's a typical layout at the moment, 30 by 30 meter, and all testing is pretty much taking place in this crash arena. You can see the light here. You can see the after crash situation. That's how it works. Location of the crash drive, so the motor. We have different ways to position this. The modern way for many new load labs is, especially if they work with a crash arena, they have the motor below, somewhere in the area of the crash arena below the floor, so in the basement. Then they would have a simple gang to the basement, and the motor would be installed down there. It has an advantage and disadvantage. So the advantage of this is clearly, if you accelerate cars from this side, you want to have, especially against the block, you want to have as little rope between car and motor, because you want to be able to the less rope you have between car and motor, the less spring you have and deflection you have in the rope. We have a solution for both, a very accurate solution for both ways how to position the motor, and so for us it's not really necessary to position the motor below the track. The disadvantages are certainly its availability. You need to go down to the basement in order to go to your motor, and even worse, if you want to do a car-to-car crash, and this one here, for example, you want to do a right-hand to the right-hand side crash, you see that the right skate is not able to run directly onto the film pit, which we usually want to have, because, as I said before, you don't want to have the free run of a car more than 1 meter. So here you have to stop the skate before it's going down to the basement, and it's coming up again. So the skate cannot run over this gap. There are other solutions how you can still control, but it's a little bit harder to do. So we pretty much we're doing both, but we like more the motor at one of the sides of the crash barrier, because then you have the possibility to have both sides of the rope going forwards and backwards over the whole length. Many customers want to do a parallel testing. So what they do is they do one test on the middle pit with a block standing here, and at the same time they already prepare for a second test on this side. So they have much more effective, and they can do 2 tests in a very short while. And so this is a big advantage of having a rope going through the whole facility. Here again, the motor at the rear end of the track, and you can see now both skates can go up to the pit cover and on the window, and you can accelerate both cars very much until they hit themselves. So you would decouple perhaps a meter before the impact point, because you clearly want to show on a photo and on proving data that there was no connection between car and rope, which is necessary for legal testing. And as I said again, here we have the possibility to prepare two tests at the same time. If you just want to prepare a high-speed test on this lane, you can already prepare for a low-speed test on this lane, and everything is fine. The disadvantage of this test is a little bit less accuracy, even though with our control systems, we still are able to control this to less than 0.1 kph. Bare friction drive. And that's something I want to explain in a very detailed way. As I mentioned before, Porsche was the first customer for this specific drive, and they already had an existing drive room. So we needed to be able to bring our new drive and the electrics and hydraulic system over here into an existing drive room with a reaction block built especially for this. So we have designed here, which is simply bolted. So the whole equipment comes like this, and it's simply bolted on the existing floor of an existing room or of an existing drive room, for example. Here you see the two ropes going into the crash lab, left rope, right rope, and there's a return rope on the other side. What we have here is a tensioner system, for which I'm going to explain afterwards much more why we need this. And we have this a motor which is sitting behind there, and then we have the friction drive where sheaves are propelling the rope depending on which direction you want to go. It's the advantage of this drive of the new drive is we can run it with both, with the existing steel ropes like you probably most have seen in typical crash barrier labs. But nowadays, our customers start working with high-strength polymer ropes. There's some advantages between for polymer ropes. For example, the weight is much less. It's a tenth of the steel rope. There's big advantages in breaking the skate, and this is big advantages because it's less dangerous if a rope is breaking. We have dual dynamic tensioners so we are able. I'm not sure how much you have seen of friction drives until now. The idea behind a friction drive is you have sheaves. The rope is running over the sheaves, and the sheaves are propelled, and that's how you propel the rope. That's why the rope is moving. In order to move the rope, there needs to be tension behind the rope. So the rope needs to be tensioned, otherwise the sheaves are just turning free in the rope. And so if you want to go in one direction, you need to have the tensioners behind the sheaves, and if you want to go to the other direction, you need to have the sheaves in front of the sheaves, the tensioners in front of the sheaves. That's why we have dual tensioners here. We are able to run during a test to accelerate a car with the system to 80 kph, and then we switch the pulling directions, and we decelerate it again to 60 kph for pre-impact braking, for example. Or if we want to if we want to break down a trolley which impacted a car after the test, we are able to have another connection to the trolley. I'm going to show this afterwards, and decelerate after an oblique test, for example, the trolley, so it's not running into the wall somewhere. This 1300 degree rope wrap, which we are talking about here, is something. It's very important. The rope wrap is showing how much force you can put into the rope, so how often the rope wrapped around the pulling sheaves, and that allows us to tension with a much. If you have a high number of rope wrap, then you don't need to have big tensioners, and then it can be quick. we can switch from one direction to the others in less than 10 milliseconds. Coming to the guide rail. If I'm talking about guide rail, this is the rail where the rope is running. And here you see, for example, the rope is running. Here's the return sheaf. One of the ropes is running in here, and the other one is running in the track. So in this configuration, you just have one track. There's no car-to-car track. It's just one track, and the rope is running in there. Our new rails, the micro rails we have, are 78 by 76 millimeters high and wide. That's very, very small. It's pretty much the same like our competitors have. That's a very typical arrangement. Here you can see this was at a lab where we already had rails on the floor. These are the old rails for the skate. This is a new rail for the skate, and the skate is running in this rail. So the skate is guided by this rail. There's a difference between the distance between the guide rails. What we introduced, and I think we were the first on the market to introduce this, is having a distance between the two rails of 125 to 130 millimeters. There's one good reason for this, and the reason is, again, visibility from the film pits from below. You want to be able to see the full vehicle from below and see how is the motor behaving, how is the structure behaving, and even how is the exhaust system behaving. So you don't want to have both rails in the middle of the lab, because this would cover much more of your vehicle. So we decided to go with a constellation where one of the rails is mostly below the wheels. So you have a very small rail only from looking from below, and you can see the whole vehicle surface and underbody and how it's behaving during the crash. Another very important reason for us why we built this is car-to-car crash with offset. So there hasn't been a good solution from my perspective until now for car-to-car with these kind of there are small outriggers on the skate, which are putting the excenter to the car before when they crash, because the big issue with this offset bars on the skate is that one of the wheels always is jumping over it, so it destroys your outrigger after each test, and the test doesn't happen like it should be. There shouldn't be any involvement of any other part of the skate or anything that keeps the wheel from turning, which keeps the car from rotating, or so on. So we looked into this and we recognized, oh, we can have much, much smaller triangles here, these offset triangles, if we have a wider difference between our wider distance between our rails. So we the maximum distance in the wider rail configuration, we need to have the maximum excenter we need to have here is 300 millimeters, 30 centimeters, and for the smaller it's 790, so it's nearly 800 millimeters. So it's more than half a meter, so it's 0.8 meters long offset arm you need for this configuration. So we run with this configurations and are very happy with this. Coming to the skates, as I mentioned, the skates are running in the rail. We have different skates for different applications. I mentioned before we can propel cars from 0 kilogram, and we have some customers who want to do truck testing with 25 tons. That's why the skate looks different for different applications. If your car is running straight, so if you have a good drive line below your car, then you don't need such a big skate, because a big skate is able to take lots of side load. Then, but here I can explain quite well how the system works. So the skate is running. So we as said before, you want to decouple the vehicle from the rope and from the skate approximately 1 meter before the impact takes place. So that's exactly where you position this triangle on, and it's this. So we have a ramp. We have a small ramp. It's a steel ramp with magnets in there, and you position it on a rail, and when the skate is running over this ramp, there's a triggering mechanism, so the post which connects to the car falls down. So the skate is running over the ramp. You can position the ramp wherever you want on the line. It's just sticking with a magnet to our rail, and then it's running over, and then it's starting to tilt and falling down. So there's no more connection between car and skate. For cars with less problems with side tracks, we have the new called 0 millimeter skate, zero height skate. This is the skate which, if it's extracted, is out of the rail. You see here, and so here you would here you see a picture where this little triangle is coming out of the rail. That's what you see when the car is pulled. But if the car is not pulled, it's fully collapsing into the rail. So you don't have any obstacle, even if the trolley, and you're going to see in videos later that trolleys tend to rotate quite a bit if they do an offset crash, for example. Very often we see a skate contacting the wheel and making the crash implausible or destroying even the wheel. That happens from time to time. And so with our 0 millimeter skate, we don't have this anymore. What we have too is a second skate. And here's one application I can show you for the second case. Now, oh, why didn't it work? Here we go. You see a trolley coming. The trolley is equipped with two skates. One skate is the skate which is pulling the trolley, and then there's one skate behind the trolley. In this configuration, after the impact, we are braking the trolley so there's no second impact between car and trolley. This is for some load cases, IIHS oblique is required. So you don't see the other skate here, but there is a connection, and the trolley is braked. Another feature we have with a second skate is this one. I told you before that we were not happy using triangles on the skate in order to offset the vehicles or the trolley. So what we are doing here is we are equipping the trolley with a fixture which is able to shift the attachment point or the rail from the very left to the very right. So here you see that the trolley is on the very left side. So that's a high over. That's for a crash where you have a high overlap. And here, for example, you see the trolley is very much on the left side. So here you see it is. So you don't need any more triangulars on the skate. You can just do this by modifying the position the trolley is running. And why do we have two of these? Why do we have two of these structures on here? Because certainly, since the pulling of the trolley is happening eccentric, because it's still pulling, we're still pulling here. We need to control the moment of inertia, and that's why we have another skate behind there. But shortly before you impact, there's no more pulling at all, because we are doing a ramp with pulling, and there's no more pulling, and then both skates deconnect, like I've shown before, collapsing fully into the structure, and the whole trolley, without running over a triangular arm of the skate, the whole trolley can impact the other vehicle and do the test as it's supposed to be. Control system. Let me give you some words about control system. So we are working with we call it Landmesser control. It's working with crash barriers for a long time. Daimler, Volkswagen, Continental, Porsche, Decra, Geely, Qatar, and Ortliff in the US. And now it's Nissan in the US, and it's Ford in Germany who's getting it, another Chinese customer too. So this control mechanism, as I said before, it's more than just giving power and just pulling the vehicle or the trolley. It's about controlling the speed and the position of the trolley over the acceleration phase every single millisecond, to be able to have a very accurate impact point impact speed, and impact timing. Here I show you, and very important is, it should never overshoot the speed. So there should never be the case where you don't approach the target speed. On the right side, you can see how our control works. So this is the set point. It is 27.8 meter per second. That's the speed you want to have at impact. And here down, you see how our tangent is running towards it. There's never an overshoot, because overshoot would mean a separation between the trolley and the skate, and that would probably cause an issue in the way how the impact takes place and in the speed accuracy. So here you see a test done at a customer in southern Germany. The target speed was 100 kph. The maximum acceleration length is 70 meters. So we knew we had to go with a very, very high acceleration in order to achieve this. So we had to go with 0.994 G acceleration. This is the maximum braking force you can do with a car is probably about 0.8 to 0.9 G. So it's the acceleration of this vehicle was worse than braking a car down. So we over the full time we had to apply 0.94 G, like 1 G acceleration, in order to get to the 100 kph speed. And we were able to do this with a tolerance of 0.1, of 0.01, because the set point was 100.30 and the outcome was 100.31. So we were able to control this very high acceleration impact very accurately. Here is something I've shown you before. Many customers need to test their autonomous driving features at the moment. And the first one is pre-impact braking. That came very early. So it's the car's recognizing shortly before an impact that the driver is not doing any attention, is not braking. So the car does a full impact, full braking, an automatic full braking. So to reduce the speed at impact. It's over. It's not that we won't impact anymore. It's we want to reduce the maximum speed. We impact the other car, so the car itself brakes suddenly, and this certainly puts the driver, because he doesn't recognize that the car is going to brake soon, in a different position in the car compared to the airbag. So if the car's braking, the whole body is going forward already, and it's already in the air in your belt. And it's a different seating position that you would have if you would just hit the wall without any pre-impact braking. That's why you have to prove that even with pre-impact braking, the belt systems with the airbag system work fine. So how can we prove this? How can we do this? Because in a crash lab, it's very hard to really use the sensors. So what we are doing is, and we're using prototypes very often, so without an active braking system. So what we are having here is we have a car equipped with a brake which we can control through remote control. So we are propelling the car to 80 kph. That's where the vehicle brakes are triggered. Then the vehicle brakes are braking down the vehicle, and we allow this to happen. And the brake is braking a little bit harder than it needs to brake, like 0.6 G, for example. And we want to have 0.5 G braking. And this means that the motor is still pulling a little bit. The motor is still controlling here to have the right speed at the impact point and to have it at the right time. And that's something we were able to prove with a very, very high accuracy, that we were able to provide this pre-impact braking on a crash lab. Looking at accuracy, I told you that accuracy is very important for our customers. And so we certainly looked at data we got from existing customer labs, and that's what you can see here. So we used 128 real crashes. That's real tests when a car is crashed against another object or into a wall, so it's a real crash test. We had 128 of those for the statistics here, and 90 of them didn't have any deviation. And the maximum deviation we had was, I think here we had 0.001 0.03 kph. I told you that 0.1 is what we tell we can do, but 0.03, so it's way less than what we wanted to achieve, what we have here. And so the standard deviation is 0.008 kph for this 128 tests we did. Showing you some of the actual projects. Complete and installed projects are Geely in Hangzhou, is Porsche in Weissach, Qatar in Nanjing, Autoliv North America, and Millbrook in the UK. And actual projects I'm going to show you is Ford in Cologne, Henan in China, and Nissan in North America, where we're just working. So the Geely project was a project where we still used one of our old drive systems, but at Geely we were responsible for the complete package of civil drawings. You see here the building efforts for the film pits and for the reaction block. You can see this is the reaction block which is being built. You see here the first works on the tracks. Here you see our very small 76 millimeters by 78 millimeter track we're going to have in the concrete floor afterwards. So here it's aligned. We laser align it over this long distance. Here you see the same, how it's running into the film pit and how it's running out. Certainly the film pit window needs to have the same track because you want to run through this window. And here you see how the workers are getting the floor done. And in the end, you see this finished lab with a very nice and smooth surface and with the right friction for legal testing. Some pictures of the motor. As I mentioned, this is the first generation of the drive. That's the typical drive like our competitors are using it. We use this at Geely those time. The Porsche retrofit was the first retrofit where we used our new design. Second generation, we say. Here you can see very good how the how this wrapping angle, which I was talking about, how we come to get to the 1300 degree. You see here, this rope is wrapped around all the sheaves. It's wrapped around in this manner, and every single of these sheaves is propelled. You see here, it's the other side. They're all connected by drives. So all these sheaves are propelled, and that's how we can propel, and that's how why we can reduce the tension force which we need here before or behind the line. We can use very low tension forces and thereby very high accelerations for this tension. So changing from one direction to the other direction is very, very quick. Porsche had another issue which we were able to help them with. This is the automated pit cover we offered to Porsche and we built at Porsche. Porsche needs to run through the middle pit, which is the pit where side crash and rear crash is happening. They need to run over those with forklifts because the building was very small. I told you 70 meters of track only. So we needed to find a way how we could have it covered if the forklift is running. So we designed something where our glass window was below this cover for the forklift, and with our motors we lifted the cover of the forklift, and then you could just slide it to the sideways, and so you would never have an open pit window, and that's something very specific for Porsche. We didn't build it since then, but if you have some of these kind of issues, just approach us and tell us, hey, that's what we need to do. Here again, you're going to see this. Here on the right side, you see the cover of the film pit for forklift driving, and here you see the film pit. It's still covered with some wrap, so it's not very nice. But here you see the rail running through the film pit. One picture again without our this is the old rail, and here you see how the new rail is installed inside the old rail. So we were able to cut the flange a little bit and then installed the new rail, our micro rail, into this. Here you see a sheave where the returning rope is going down to the pit floor. So Qatar in China, we did something very similar. They had an old barrier system, which we fitted with our new drive system. That's number the new drive system generation. And here it's coming the third generation of the drive system, where we don't need the sling profile. Here we have a rubber belt. You see this here. We have two drives, and where the sling is going around, is wrapped around, and then they're both connected by a rubber belt system. It is working at least as good as a Porsche system at a lower cost and a better price for the customer. Autoliv North America, a very similar issue, very short track, very high speed acceleration they needed to do. The Millbrook Proving Ground is a European lab in England where we did the same. They have a dual approach. So the first step we did is just building the motor and the drive system, and the next step will be coming up the year now that we build the new rail system with new skates. That's something we can discuss with you too. So many customers cannot afford to have the lab down for 3 months because they have testing to do, and they can afford 2 weeks only or 4 weeks only. And so what we offer is, the first step is we change the drive system with all the control system so that the accuracy of speed is already there. And in the second step, we can retrofit the next summer vacation, for example, we can retrofit your lab with new rails and with new skate, so then the accuracy of impact position is there. This is something we can discuss, or even other constellations. Okay, upcoming projects. Here's Ford system. I told you they had this old crash barrier building, and now we are building the new one. But certainly the whole building and the whole length is going to be refurbished with new rails, with new technology and everything. And here's the site, the track where they can do angular track impact. The Henan Institute in China is an interesting one because here we use the same technology and the same motor to run with 25 ton vehicles. So this is 25,000 kilograms, and certainly we need a longer track because the force we can increase the force quite a bit, but you still need a longer track in order to hit at the impact speed you want to have. And this is North America, something I can show some pictures. So it's the complete track. Yeah, so Nissan North America has a complete greenfield facility. So everything is new there. We are doing all the technology for this plant. Certainly the civil work is done by another company, but we bring all the crash technology, and we are really happy to have Nissan as customer. And what they have is something very special. They have 2 parallel crash positions because they need to do more testing. They have one for low speed testing and they have one for high speed testing. And so we can do different constellations here. We have 2 motors, we have 2 drive systems, and either one motor is driving the upper and the other one is driving the lower one, but we are also able to do car-to-car crash with 2 different speeds. And that's very important if you're doing testing where you want to test an accident that happened in reality. Both cars didn't have the same speed, and typically car-to-car crash can only be done with the same speed. But here we have 2 motors, 2 drive system, so we can really reproduce the constellation like it was in the real crash scenario outside. So it's really what I showed you here in this presentation. I hope it came over quite okay. That we can do both. We are happy to install a brand new lab, while we are at least as happy to retrofit an existing lab with the technology you need, and not just with technology we have, but with what you need. And we're going to listen to you. We're going to talk to you. We come back with proposal from our engineering, and we're going to find a good solution which allows you to do the testing of the future and which allows you to retrofit your existing lab in order to have the most modern lab afterwards without the big investment of a greenfield lab. Thank you very much. I think this is the presentation I wanted to give.
Thank you, Philip. If you have any questions, please type them into the chat box in your control panel. Meanwhile, we have two questions, Philip.
Let me read the question first. You sent me two questions with in the NCAP, at what speeds are passenger vehicles are crashed into the rigid barrier that covers the full width of the vehicle? So I think it is not just NCAP we're looking at. It's the what I can see at customers is a whole variety of tests they have in their testing matrix because they want to be safe above and below the legal load cases. So my answer would be, I think if you build a lab now, you probably want to be able to run with a 3.5 ton vehicle up to 100 or 105 kph. That's a 100, if 110 because there's one load case which is 100 already. So make it 110 kph, and you should be on the safe page. The second question is, what is the track length for a testing facility to meet the entire range of testing capability necessary to cover? Again, pretty much the same answer. I've shown you that you can even run with a 70-meter lab, you can accelerate a 3.5 ton car to 100 kph. This is nothing your dummy wants to see. This is something for structural testing. It's okay because for structural testing, it doesn't care how quick it got to 100 kph. But if you want to do tests with a dummy, that's nothing you want to do. So if we are saying test with a dummy, you shouldn't exceed 0.3 G. And for this reason, until for speeds up to 80 kph, 0.3 is reached in 120 meters lap length. And certainly if the big advantage is if you have a crash area like I've shown in the middle of the building, like crash arena, then you have even the possibility to accelerate a car over 240 meters because it's twice 120 meters. So if you're running onto the full track, that's somewhere where you can easily have a truck tested, which is 15 tons and getting up to 100 kph. That's easily done. Any more questions?
I don't think, Philip. So please feel free to contact us if you have any questions later. So great. Thank you, everyone. We appreciate you being here. Thanks again for joining us today, and we'll see you again next time.
Okay. Bye-bye to everyone. Have a nice weekend. Bye-bye.